introducing exponents for the first time. So you may have seen exponents before in your life, in your mathematical lives, but I'm going to go over it from the very beginning. So an exponent represents the number of times a number is multiplied by its base. A little confusing. So let's do this in a little bit more detail. So let's say I have 2 to the power of 3. So you would read that as 2 to the power of 3. This whole thing is called a power. Specifically, the 3 is your exponent, and the 2, we would say, is your base. What does this mean, 2 to the power of 3? Or you could say 2 cubed. Well, it's the number of times a number is multiplied by itself. So that means 2 is multiplied by itself 3 times. So we get 2 times 2 times 2. So I wrote out 3 2's there. 2 times 2 is 4. 4 times 2 is 8. When in doubt, expand it out. It's a saying we'll use lots within the exponents or powers units. This form, 2 times 2 times 2, is what we would call our expanded form. So whenever you're stuck in this unit, expand it out. When in doubt, expand out. So within exponents, we can go into a little bit more detail about the base. So the base is only what is directly in front of our power. In order for it to be a negative, the negative needs to be in brackets. So notice in this one, we have negative 2 to the power of 4, but that negative is out front. So I like to say that negative is hanging out. So here, we would write out our expanded form with the negative, our 4 2's all in brackets, and then 16. So if you wanted to, you could kind of include a second step here where it's like negative times 16, which gives us negative 16. Versus on this second one, the negative is here in brackets. So then I'm going to repeat that negative. So we have a negative, 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 which ends up giving us a positive 16. So I want you to pause the video for a second and try and answer these next 2 questions below. And then check your answer with the video. So in this first one, negative 3 squared, that negative is not, we would say it's not directly attached. You could almost think of this as like subtracting 3 squared. Well, 3 squared is the same thing as saying 3 times 3, so then I would get negative 9. Versus on this one, I have negative 3 times a negative 3. Negative times a negative gives us a positive 9. Remember, you don't always have to write the positive sign. You could just write 9. Positive is implied. Now let's look at negative 3 cubed versus negative 3 in brackets cubed. So in this first one, it's like negative is hanging out, and then I get 3 times 3 times 3. 3 times 3 is 9. Well, 9 times 3 is 27. That negative continues, so I still have a negative final answer of negative 27. In brackets, I get negative 3 times negative 3 times negative 3. I'm going to show an extra step here. Negative times a negative gives us a positive 9, but that positive 9 is then multiplied by negative 3, giving us negative 27. So in this case, we actually end up with the same answer, even though the question was written ever so slightly different. This is especially important, these bracket placements, when you're putting it on your calculator too, if you're using your calculator. Perfect squares are something we will reference lots within math. So a perfect square, well, a square is the same length on both sides. So this square is a 4 by 4 square, giving us a total of 16 squares in the middle. So there's numbers that we would say are perfect squares in math. So let's go through our numbers. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. All of those answers, so everything on the right side column, those are our perfect squares. So let's continue all the way up to 200. So 6 squared is 36, 7 squared, 49, 8 squared is 64, 9 squared is 81, 10 squared is 100. So again, the second column is our perfect squares. 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is 196, and that's going to be our last one, less than 200. Really, I expect you to know less than 100, those perfect squares. What is a perfect cube? Well, a perfect cube is simply when the number is cubed, that answer. What's kind of interesting, 1 cubed is 1, 1 squared is 1. 2 cubed, 2 times 2 times 2 is 8. 3 cubed is 27. 4 cubed, so 4 times 4 is 16. 16 times 4 is 64. So again, on the right side, those are our perfect cubes. I only would expect you to know those first 4. I want you to try and complete this table on your own and see what you notice. So if we have an exponent of 4, pick any base. Let's choose easy bases like 2 or 3. Write out your expanded form and write out your value. What do you notice about the power of 0? Again, do this on your own. Pause the video, do it on your own, and then you can check your answer with me. So when you fill out your table should look something like mine. Your numbers might be different, but you should be noticing a pattern. Remember, back in the day when people were just discovering math, they came up with exponents. This is something they decided. So when they were coming up with what an exponent meant, they were like, okay, so what then will exponent 0? What would that possibly mean? So they started looking at patterns of what rules they set in place. Well, if I look at this, if I move down my table to go from 16 to 8, I'm going to divide by 2. To go from 8 till 4, I'm going to divide by 2. Again, divide by 2. So therefore, I have to get this next one, divide by 2. So to divide by 2, I'm going to end up with 1. If you did this with any number, you're going to end up with base 1. So basically, anything to the power of 0 is 1. Okay, I want you to try this next one and see what you notice. So you may have noticed a pattern here when you filled out this table, and try and make it in the simplest words as you can to see if you can help yourself predict what value for base 10 powers or base 10 exponents will be. The simplest one for me is that the exponent is equal to the number of zeros. Number of zeros, specifically trailing, so behind, 1. So there's, for this first one, there are zeros behind the 1. And the second one, I have a 1, so there's 1 0. There's a 2 here, so I have 2 zeros, and so on. These are 2 really good simple investigations that you just did. I'm going to stop there, and we will come back to prime factorization later on.